Okay, finally, we can talk about Hawking radiation. Uh, it's related to the phenomenon of quantum fluctuations. The quantum uncertainty principle, delta E, delta T is greater than Planck's constant, implies that the process can temporarily violate energy conservation, okay, provided they do so for a sufficiently short time. Uh, Such a fluctuation turns empty space into a medium with particles and antiparticle pair appearing and disappearing. But in a normal circumstance, such energy non-conserving process cannot survive on a macroscopic time scale. So, but only on a microscopic scale, there's energy conservation for a short time as long as the product is not too small. Consider the simplest case, the creation of a particle-antiparticle pair from vacuum, from nothing. If the pair are to persist, not to prompt anarchically back into vacuum, energy conservation requires, say, this equal relation, this start from nothing, so therefore zero, to for one particle energy and the antiparticle energy. Now, if both particles could reach R equal infinity, here the infinity, okay, then E plus and the E tilde energy at infinity would be their energies measured by observer at infinity. Such energy must be positive, so the above quality cannot possibly be satisfied because you can't have two non-zero positive quantity equal to add up to zero. Hence, so it's only the temporary creation and destruction particles. So they are called usually virtual particles because they can't persist into a macroscopic scale. Hawking pointed out if such quantum fluctuation takes place near the event horizon, the virtual particle can't become real because in such situations, energy conservation can be maintained permanently. Okay, the, the, the statement which says in positive energy conservation turns out if it's fluctuation near the event horizon, it can be avoided. If we suppose a pair creation of nothing to a particle, antiparticle, and then knock it back into if this all these quantum fluctuations take place near the event horizon, this is supposed the cylinder is supposed to this is supposed space-time diagram. Of course, space is only two dimensions, and time is going this way. So the event horizon, the Schwarzschild surface, is represented by the cylinder. Okay, and nearby there's particle, antiparticle annihilation, the creation and annihilation. Okay. If it takes place sufficient close to the event horizon, one particle can be outside and eventually travel to infinity. The other can be inside, falling to singularity. So this goes to infinity, and this goes to infinity, but the other one goes falling inside. Recall discussion of causal structure of event horizon. The roles space and time are interchanged because space and time belong to the same vector, the same tensor, the different component of the same tensor component. Okay. In the same way, because energy and the momentum are different component of the same tensor, the role of energy and momentum can be interchanged when going across this Schwarzschild surface. So the energy component inside the horizon takes on the property of momentum. And it's possible for energy of particle to be negative, have negative energy inside the event horizon. Now, if energy is negative, then the conservation relation can be satisfied on a macroscopic time scale because to a distant observer, the black hole, by swallowing a particle of negative energy, can emit a particle with positive energy. So therefore, if you see all these particles are coming out, so that's Hawking radiation, that's Hawking effect. So simply, the key point is that the road road change of energy and momentum, just like a space-time road change in the uh, because energy and momentum belong to the same tensor, and time and radial distance belong to the same uh, tensor. So we're not talking about how Hawking arrived at this in the context of quantum field theory and curved space-time. Now remember we said radiation field can be regarded as a collection of oscillators. Whether it's quantum or classical radiation field, it can be decomposed into plane waves. The coefficient expansion, then you see, because wave equation obeys simple harmonic oscillator equation, so therefore we can regard radiation field as a collection of oscillators. So when we talk, that's what is classical quantum, but in particular, quantum field means it's a collection of quantum oscillators. Okay, it was oscillators described by quantum mechanics. So, and if you had a class quantum, the first thing you learn is harmonic oscillator in quantum mechanics. And those quantum oscillator energy spectra has discrete, even in space levels, can view states with a particular number of energy quanta. These quantum states are related by raising and lowering operator, also called ladder operator. So therefore, quantum field theory have the natural language to describe the creation and the annihilation particle, the emission absorption of particles. Now, in a curved space-time, the natural decomposition is still plane wave, but now with respect to coordinates that encodes curvature, like in the crisscross coordinates. Okay. Then the vacuum of a quantum field system, when viewed by a distant observer, which of course distant observer far from sources in flat space-time, the vacuum state can view a state with distribution particles. Okay. In this way, Hawking obtained the particle distribution result just by decomposing field in the critical coordinates. That's the number distribution is equal to e to the 2 pi c e over h bar. Sigma is the gravity, black hole gravitation, surface gravity. Okay. Now you compare this distribution to the black body thermal distribution, so it has the same form. So therefore, due to quantum effect in the surrounding space, a black hole surface gravity sigma star radiates particles as a perfect black body temperature, K. And because you notice this 1 over uh, 1 over uh, 1 over sigma star here is 1 over t. So therefore t and sigma are proportional to each other. So kt is equal to sigma h bar sigma over 2 pi c. Okay. So that's the relation we're looking for. Remember we say somehow the surface gravity behaves like temperature. Now here shows precisely they are related and the proportion constant fixed. Okay. Now if you plug in the expression for surface gravity in terms of Newton's constant mass, and then knowing the fact that 2 gm over c squared is Hawking radius, so this can be written as hc over 4 pi r star. So you can dimension make sense. Remember, hc has dimension of energy times length, and now we have denominator is length, so therefore this whole quantity is energy kt. And also somewhere in natural, if this energy length divided by length, so natural length is the Schwarzschild radius. So it's not, it makes a lot of sense that kt have this expression, how it's related to surface gravity of the black hole. Now the fact that temperature is inverse proportional to the mass, so therefore the Hawking radius for a large astrophysical black hole, a huge M, so therefore the temperature is very low. So the compared with the energy gains by infalling materials, is totally insignificant. However, if they are so-called mini black holes, the loss of mass decreasing mass will increase in temperature, and which will cause the radiation to go even faster. So it's possible to have a complete evaporation of mini black holes. So now we'll talk about entropy. Given the Hawking temperature, we just talked last slides, and then one can find the entropy through its definition. The entropy ds is equal to dE over of temperature. Now, naturally, we can identify mc squared as E, so put mc squared here. So therefore, ds divided by Boltzmann's constant, so it's just this expression here, Cm E equals or kT, and then put in the Hawking temperature here, get this. So it's so therefore the differential of entropy is related to differential of mass squared with proportion to Newton's constant. So just by integrate, you can get the expression for entropy, and so this is already perfect differentials, just m squared. Okay. Now you can multiply Newton's constant, divide by Newton's constant, and then you have an h value over here. So this expression, of course, is for the Schwarzschild radius square. So I'll multiply by, take the 4 pi, so that's equal to the surface, the black hole area divided by 4. Now, if you look at this expression just 1 over Planck length squared. Okay. So again, it makes a lot of sense. I have entropy in units of Planck's, in units of Boltzmann constants. Therefore, the left-hand side is dimensionless, so I should have a dimensionless on the right-hand side. And from here, we say this is proportional area. Okay, so therefore it must be divided by something that has dimensional area. So natural dimension you have is the Planck's length. Okay, so again, really acceptable factor 4. This you expect that entropy have this some ways this if you can show that the entropy is related to area. Okay. So this results the entropy is proportional to area with this some way natural proportion constant is a shocking result. Why so shocking? Because entropy is an extensive variable in thermodynamics. So expect entropy to be proportional to volume, not to the area of the system. Okay. So this is really surprising. And that led to the proposal that in quantum gravity, the description of a spatial volume is somehow encoded on its boundary. Okay. For instance, all the information about black hole is encoded on its event horizon. Okay. This idea has been elevated to a fundamental principle of quantum gravity, the so-called holographic principle. Hologram, you can use the information on the surface, and it can get 3-dimensional pictures. And what do you mean? This is elevated is proposed by Tuft and later also by Lenny Susskind. And the idea is just like Einstein proposed the equivalent principle. In order to focus on this and try to extend it to get more information out of it, that's the reason you want to have elevate something to a principle to guide you for future discoveries. So now we want to, knowing the expression of entropy in terms, and then from we learned from Boltzmann, the second law of thermodynamics was amenable to precise mathematical treatment. The macroscopic notion of entropy is related to counting of the composing microscopic states, so-called the compression. So the entropy is equal to proportional log of the compression, and proportion constant is Boltzmann constant. This you can regard probably in some sense it's a good candidate for the second most famous equation in physics besides E equal to mc squared. That's a, uh, so the question is, what would be the microscopic statistical description of a black hole that corresponds to this entropy? So we need a microscopic theory, quantum gravity. In fact, black hole entropy will provide a check on any viability of any proposed quantum gravity theory. In that sense, the string theorists has been greatly encouraged by some success they had in recovering the entropy by counting the number of ways a black hole can be formed in superstring theory. Superstring theory is a candidate quantum gravity theory. So the takeaway from lecture 20, the Planck unit system, mass, length, times in terms of Newton's constant, Planck's constant, and velocity of light, or Einstein constant, is leading to extremely high energy and short distance time as being the natural scale for quantum gravity, which is union of GR to quantum mechanics. Quantum field theory is union of special relativity with quantum mechanics and does not require Planck's scale for its effect to be significant. But and quantum theory in a curved spacetime means classical description of gravity, while quantum description of other interactions, as in the derivation of Hawking radiation, which is brought by quantum fluctuation around black holes' event horizon. The particle inside the black hole can have negative energy. So that's through the study of Hawking radiation, the relation between temperature and the surface black hole surface gravity and entropy and area, black hole area, are firmly established. They will constrain any quantum gravity theory. The next lecture, the next series of lecture, 10 lectures, the Einstein has always understood that a major application of general relativity will be universe at large. So next 10 lecture will be on cosmology.